we've seen how the vector function, and of course we haven't defined a vector function yet, but we've seen how the parametric functions x of t equal cosine of pi t, y of t equals t squared yield these values of x and t. So now all we're going to do is we're going to plot these points on a graph. So here's x, here's y. The first point corresponding to t equals 0 is 1, 0, so we plot the t equals 0.10 here. Second point is 0, 1/4 or 0.25, and this point is plotted. It comes out here. This point, negative 1, 1, corresponds to t equals 1, so our t equals 1 point is negative 1, 1. It's here. Our t equals 2 point is 0, 9/4 or 2.25, so t equals 3/2. Our point is 9/4. And at t equals 2, we're going to get the point 1,4. That's actually up and off of our graph here. If we were to sketch a smooth curve through these points, it might be a little bit mysterious whether the curve is concave up or concave down as it goes from this point to this point, and just how that concavity changes and just exactly what the shape of the curve is. However, the curve that we have here is a reasonable approximation for right now, and we're not going to worry too much about the concavity. Those are subtleties that we'll be able to analyze later. They aren't too difficult, but we postpone that discussion for a little bit later. Okay, now what we've done is we've essentially defined a vector function. The vector function is f of t equals x of t times I plus y of t times j. I and j are the unit vectors in the x and y directions, so x of t times I is simply a vector whose magnitude is x of t and whose direction is the direction of I. To that we add a function whose magnitude is y of t and whose direction is the direction of j. I can sketch the f of t functions for t equals 0, 1/2, 1, and 3/2. If t equals 0, the f of t vector will be f of 0. It'll be this vector. Now the f of 1/2 vector is going to be just a little short vector here, and it's so short we can hardly even label it, so I'm not going to bother trying. The f of 1 vector goes from the origin to this point. The f of 2 vector goes from the origin up to this point. And I'm sorry, that's not f of 2, that's f of 3/2. Let me kind of fudge a little bit here. Okay, so that's f of 3/2. Doesn't look too good, but you get the idea. And f of 2, if I try to sketch that vector, it's going to go through some of my labeling, so I'm not going to do that. We can see then that if this is the curve that represents this vector, we have a series of vectors. A vector from here to here, then a vector from here to here, a vector from here to here, and so on. And we could sketch those vectors. Let me use a contrasting color here and just sketch a series of vectors. Okay, we got a vector here, a vector here, a vector here, a vector here, and then we have another vector comes back here, and a vector that goes this way. And these don't represent any particular time interval, but we see that we can imagine a vector rooted at the origin whose length starts out as 1, and as we proceed in time, the tip of the vector follows this curve. So the vector gets shorter here and shorter here, then it starts getting longer and longer, and even longer and longer, and of course its angle keeps changing. Its angle goes from here around to here and then starts coming back and going up here. We can represent that vector function as f of t equals x of ti plus y of tj, cosine of pi ti plus t squared j in the case of the function that we're observing here. And we can write f of 0 is cosine of pi times 0 times I plus 0 squared times j. Cosine of pi times 0 is just 1. Excuse me, so f of 0 is just the I vector, and that's really what we've sketched here. F of 1 is the cosine of pi times 1I plus 1 squared j. And the cosine of pi is negative 1, so this gives us negative I plus j. Our vector, f of 1 here, is negative 1 unit this way, 1 unit this way. Now I haven't really used equal scales on my x and y axes, so that the j vector might look a little shorter than the I vector, but you should get the idea.